Okay. Let me just check if the audio is working. All right, I just got confirmation. All right, so this is day 2. We're going to be deploying using Streamlit instead of Flask. So deploy a linear regression model using Streamlit. So I'm hoping to finish this really quickly since the code for the linear regression model is going to be the same as yesterday. So all I have to do is pretty much create the UI using Streamlit and get all of the backend services working. Deploying the train model as a REST service. So yeah. All right, let's get started. So I was looking into this chapter earlier this morning because I just wanted to get through this really quickly. So most of the code is still in Python. Streamlit is just like another basically library. Instead of Flask, we're using Streamlit. Is the fact that we have to write little to no HTML. So all of the HTML and CSS is taken care of in Python. And if you don't really know HTML that well, or if you don't know CSS well, this works out pretty well for you. And it's also really, really fast because you can just start coding everything in Python and finish an entire website with Python. So let's make a folder. We'll call this Streamlit deployment. So first we're going to do the linear regression model, and then we're going to, if we have time, we're going to do the deep learning model. We're going to deploy the same thing on Streamlit. We're going to create an LSTM model and deploy that. Not sure if I'm going to have enough time for this today, but we'll try to get as much done as possible. So let's get rolling. So created a folder. Now let's create a file. Let's call this Streamlit app.python. Cool. And I think what I'm going to do is I'm going to copy the data set. Oh, that's the pickle file. I'm going to copy the data set. Paste. All right, cool. So I know it's a little... ideally, what I would have done is maybe created another folder called datasets and use that location. But should I actually do that? Maybe we'll do that. It'll let us keep all of our code in one location. So I'll delete this. And I will put the file here. Paste, where's paste? There we go. This just means that it's going to get a little annoying when we're specifying the path because it's not in the same directory, but we'll deal with those issues as they come by. All right, cool. So import Streamlit. I'm not sure if I have to pip install Streamlit, but we'll test it out and see if it works. And as SPD, import numpy as np, import joblib, and import Streamlit. Save this. CD into my directory. Challenges, 100 days of ML. And Streamlit. Okay. So Python, Streamlit. Okay, yeah. I'm going to have to pip install. Sometimes you just want to double check what the pip install is. Even if it's just like pip install Streamlit, you want to double check at pipe pipy Streamlit. Because some people, they change the name by a very small, like, maybe instead of an E, they put an A or something like that, and then it's malicious software that you can download accidentally onto your computer. So you want to be very careful what you're downloading off the internet. While that does that. Next step, we're going to import the regression model. Okay, so what they did is just copy the pickle file. You know, I could honestly do that too. Instead of having to write the whole code to like save the pickle file, we could just copy it. Let's copy, paste it into our directory. Boom, we're done. So now what we have to do is open up the model in this Streamlit application. So model, and we're going to use the open function, linear regression model.pickle, and specify write back. Then we'll create our we'll load in our model using joblib. So basically open you're reading the file, and with joblib you can load the actual model into an object. All right, cool. Next step is to define a function to make predictions. All right, let's do that. Define LR and prediction. Our variables are of course going to be different. Let me double check what they are. Alcohol, volatile acidity. Where were the short forms? Here we go. I'll just copy over this. And those are our variables. So inside this function, we're going to be converting all of these parameters into a NumPy array, so we can feed it into the model. Boom. Okay, now we're going to reshape it. Prediction array dot reshape. So I was actually stuck on this for a very long time yesterday. While I was editing, I realized I was stuck on this problem where I wasn't reshaping it and it wasn't providing the right output for like about 20 minutes. So sometimes you do just get stuck on very simple problems. As type, here it's casting it to an integer. I really don't think this matters too much, but we'll see. We'll see how it goes. Model and then prediction. And then we're going to use the model to predict using the predict method. Okay. Finally, we're going to return the value, which is model prediction. Okay, so that's our prediction method. Ideally, you want to document everything as you go. So you create doc strings. Sometimes in Visual Studios, I know Visual Studios has like a shortcut where if you type in the doc strings, it automatically formats a bunch of stuff for you, doc strings. Because I remember during the presentation, there was a link, what was it called? Made with ML. This website had basically resources for Python documentation. And we'll check that out really quickly here. So, where is it? Where is it? Versioning, pre-commit, documentation. There we go. So, if we scroll down here, it tells us about doc strings and how to add doc strings to our code to make it more readable for other users. If suppose you're in a production environment, you're working for a company like Google, you would have to sort of like document your code. So like your coworkers and other people, like your boss, could understand what's going on, how to use the the function and what it does. So docstring is also pretty neat because if you are creating basically like a documentation, all of the doc strings for each method comes into a neat package, and then you can display it. We'll be doing that later, I think. For now, let's just focus on getting these models deployed. I do eventually want to learn how to properly document all of my projects. So it does make it neat, and it's also very nice if you're displaying your projects to other people. Okay, let's get back on track. So next is the run method. It says it does the same thing as Flask's app run.run. Right, okay, so I think in this method, we're going to be creating the HTML with 1, 2, 3, 4 text inputs for our different variables. And then we're also going to add a submit button. And once that submit button is clicked, we want to call our model and display the prediction. And you could see the difference visually. Like, we had to write so much more HTML in the previous method where we're using Flask. We had to write all of this HTML, which just got condensed into like 4 lines of code. And it comes with pretty good CSS, which you don't even have to specify. You could even specify the style if you wanted to in Python. So all of this code just gets condensed, and that's pretty neat. I think that's the fun part about Streamlit. I don't know what the performance hit is, because considering, I think HTML should be faster to load. Because what it has to do is basically convert this Python code into HTML. It's just a high-level abstraction of what we're coding. Okay, linear regression model, HTML temp. See, I was kind of confused what actually this does. I'm still not too sure. When I was looking at it in the morning, HTML temp, and it gets converted to Markdown. Let's read the documentation for this. Okay, Streamlit, and then what is it? Markdown. API reference. Magic commands. Write Markdown and data. That's not what we're doing. Dot text. Dot Markdown. Here we go. So display string as Markdown. Okay, that makes sense, I guess. So I think here the string is empty, or it's an empty line. Interesting. Markdown. HTML template. Okay. Streamlit. So now we're gonna get our variables, which is alcohol, and we need a text input for this. Alcohol. And then next, I think it's volatility. Let's copy paste this to make it go faster. Volatile acidity. Sulfates, I believe that's next. Yep. And finally, total sulfur dioxide. And we'll name that DIO. Okay, cool. So we have our text inputs. Now we need our button, and our prediction, of course. Prediction PION. For now, it's going to be an empty string because we don't have the prediction yet. Okay, so if the Streamlit button, which is named predict, is pressed, I believe. So if it's pressed, this value is going to become true, and we're going to enter in the if statement. Prediction is linear regret prediction. I think linear prediction is, yep, the method for the prediction model. We're going to pass in our variables, the same variables. I can just copy and paste this here. Same variable names, I mean. And then outside of the if loop, once we come out, we can display success. The prediction by model is, and we're going to use format to display the prediction. Cool. I think, yep, that's it. And we have to just write down this. And in our terminal, we just have to run the Streamlit. Streamlit. Our Streamlit is called stream lit app.py. Wait, I think there's a run somewhere here. Yep. Streamlit run Streamlit app.py. I think I'm going to skip out on providing my email. Awesome. All right, that was so quick. And we could just enter in random values for this. I'm not too sure if the model is very accurate. I think we were testing it out yesterday. The accuracy was pretty low, but I mean, you could always change up the model and have a different model instead of this one I chose. But the main like goal for this is deployment and having like a website to actually test the model. So this is like a full application. Let's put some data in here and test it. Got an email. All right, cool. I'll check that out later. Okay, alcohol. Okay. What would be an easier way to do this? Fixed acidity, volatile acidity. Do we need volatile? Yeah, we need volatile acidity. 0.27. And then we need total sulfur dioxide, which is number 1, 2, 3, 4, 5, 6 from the end. So 1, 2, 3, 4, 5, 6, 45, I believe. Oh, geez. And sulfates, which is number 3. 1, 2, 3. 0.45. Predict. Oh no. Let's see. Invalid literal for int. As type int. Okay. Let's just try to remove this and see if it'll take in the array. I think I have to rerun the... Oh, and I have to provide alcohol, which I totally forgot about. It's number 2. 6, 8.8. I should probably store these values somewhere before I forget. I'll just make it here. So 8.8, 0.27, 0.45, and 45. Let's predict. Okay, there's some error going on. We'll reload the Streamlit app. Copy paste our values. Okay, so there's some sort of data type problem again. Say sparse dot. Just save it. Let's just check what we did in the Flask app. So we converted to a NumPy array and then we reshaped it, and then using the model we predicted it using the reshaped NumPy array. So I believe we're doing the same thing here, except I'm passing it as an array here. Oh yeah, it's a list. I'm passing it as a list. That's fine. So convert it to a NumPy array, reshape it 1, -1. Do I have to round the result? Model prediction, return. I don't think it should matter because Python, you can return any sort of data type and print any data type. There's no really restriction on what it has to be. So let's reload this. Future warning. Recommend you convert the array to float data type before using it in scikit-learn. Your array as type np float. Okay, so that's why I think this was happening. So instead of int, let's use np.float 64. Cool. Copy paste the values. All right, awesome. So when you hit predict, you can see that the result here says prediction by model, and it gives you the predicted value 5.196. Suppose we enter in an invalid answer, it will give us a value error. So this is pretty neat. I mean, compared to writing Flask, where you have to take into consideration of all of these variables. Here in Streamlit, it automatically does everything for you, so you can focus less on the front end and more on the model development and the backend process. So if you're not really like a great front-end engineer, you don't know a lot of front-end technologies, this would be pretty neat for you. And I think I'm definitely going to be using this in the future, especially for hackathons, where if you want to develop like an application really quickly, but most of the work is actually in the backend, right? You could develop something super simple, super good looking, and very interactive as well, really quickly, under the time limit for the hackathon. So I recommend learning Streamlit for that. Okay, so I guess that pretty much concludes everything that I set the goal for today, but I'm going to extend it because I finished this in like 20 minutes. All right, so here's what I'm going to do. I'm going to take a little bit of tomorrow's work and put it down here. So I think what's next is the deep learning model, which is going to use the LSTM model. So I think this is going to take a sufficient amount of time because, again, they don't really list out which data set they're using, which makes it difficult for us because we can't follow this code example. We're going to have to kind of pre-process and tokenize and embed all of the words by ourselves. For that, I'm going to look at data sets for, I think what they're trying to do is a sentiment classifier. Deep learning model, deploy using Streamlit, LSTM-based neural network to predict the sentiment of a given review. So basically just predicts either if it's a negative connotation or a positive connotation. I think I did this before actually. Wonder if I... Where's my website? Sentiment analysis. Yeah. What did I use for this? Scikit-learn. Right, this is not what we were trying to do. We're trying to build an LSTM model, not a logistic regression model. So can't use this. All right, let's look for data sets for sentiment analysis. TensorFlow datasets have pretty good datasets as well. So I'm going to look at TensorFlow datasets. TensorFlow datasets. Where is it? Where's the list? Catalog. Text. I need it for sentiment analysis. Image classification, question answering, structured, summarization. It would be better to just search it on the internet. Sentiment dataset. Well. Okay, so this uses the IMDb large movie data set review. They use this data set. What model do they build? All of this is pre-processing. Let me expand this a little bit. Show me. Create the model. They're building a sequential model. It's not ideal because want an LSTM model. Okay, I mean, I think for the most part we can follow it up till here. And we're going to have to change the embedding layer. And all the pre-processing should be the same. So here the embedding is in this shape. They had embedding as 50. Here I think we're using 16. I mean, we could always reshape it based on what our data set size is. So we had an LSTM layer, and then we add a dense layer on top of the LSTM. And there's the embedding input. Just want to make sure this works before diving into it, because changing the data set in the middle would be painful. TensorFlow Hub, RNN. Let's take a look at this instead. So here, what type of model are they using? Recurrent neural networks? Bidirectional LSTM. That's cool. That's cool. This could work. They're using a variation of LSTM, which is bidirectional. They have an embedding layer, 64. They have an encoder. The encoder is built into the model itself, which is pretty nice. Input pipeline. Train the dataset, create the text encoder, preprocessing, text vectorization. What do we use here? Check the differences. We use a tokenizer. We use the embedding layer here. And pad sequences. Honestly, I don't think it should be that different, right? The model shouldn't matter. It's just the deployment process. That's the important part here. So keeping that in mind, let's begin. So here in Streamlit deployment, I'm going to create another folder for linear regression. Move these files inside. And then now we're going to do the LSTM model. Cool. In LSTM, let's create a file. Let's call this model.py. LSTM model. Model.py. All right, and then we can follow this guide from TensorFlow. Here they just say recurrent neural networks, but if you actually go to the model they're using, it's a bidirectional LSTM. I mean, LSTM is a variation of a recurrent neural network, so it does make sense. So import numpy as np, import TensorFlow datasets as tfds. Import TensorFlow as tfds.disable progress. Blah, blah. I don't really think this line of code matters, but it's okay. Matplotlib to visualize our datasets. PyPlot as PLT. And then we're going to create a helper function to plot the graphs. So here history actually comes from after training the model, I believe. So that's pretty cool. History dot history. So this plot will allow us to evaluate our LSTM model at the end. History, and then plt.xlabel, label for the x-axis. I'm gonna plot epochs versus the accuracy, I believe. Oh, and our metrics can change. It can be epochs versus accuracy. It can also be epochs versus loss. And I think we'll plot both of them at the end. And since this is a very dynamic function, we can pass in whatever our metric is and call the function again. Legend metric plus metric here. Okay, cool. I'm just going to start labeling things. Helper function to display metric graphs. Cool. So now we're going to set up the input pipeline. Load the dataset from TensorFlow datasets, the IMDb reviews, train dataset split to train test categories, and then examine the shape. So here, input pipeline. Data set and info. Get that from TensorFlow datasets. IMDb reviews. Lit info. As supervised. I think this is just defines the dataset as a supervised learning dataset. Supervised. So there's a difference between supervised and unsupervised learning. So here we want to do supervised learning. So that's where we're going to be specifying as true. Now let's split it up into train and test. Train test dataset, dataset, train, dataset, test. And then train dataset dot element spec. Right, so we're not doing this in Jupyter, so we should print the value. And I think we should include, I think this should open up matplotlib. If it doesn't, we're going to have to include like a line for inline, but we'll get to that later if that happens. Okay, so next we set up the buffer size and the batch size. Oh no, we have to do this. Initially returns a dataset of text and labels. And we're just going to print it out just to see how it looks like. Okay. Train dataset. Take one of the examples, and we're going to print it out so we can visually see what's in the dataset. NumPy. Label.numpy. All right, and I think if we run this, we should be able to see. Well, let's stop the Streamlit app first. And then we're going to cd backwards into, oh no, I should not have done that. cd into LSTM. And run our Python model. Oh no, I just remembered something. I have a problem running TensorFlow because I tend to use the GPU while training. So I'm going to have to use Docker to build this model. That reminds me of things. All right, I'm going to take a quick short break for now. Drink some water. Yeah, word of advice, I guess, if you're following 100 days of ML, be consistent, remember that, and always make sure you're planning a day ahead. So you always have something to do, right? And always try to follow a guide. Sometimes it may be a textbook, it may be some sort of resource online, but have like an overarching like goal. Like, what do you want to get done? So you always know like what to do. Otherwise, it's really easy to get lost with your challenge, and once you do that, it's kind of hard to like stay motivated. Okay. So the Docker specification is very specific. I think I listed it out somewhere here. Might be on my GitHub. If you do want to follow along with what I'm doing, you could always check out my GitHub repository. It's always going to be updated on every day. And you could also follow the series on YouTube. Let's go to Text Summarizer. This is a project that I built recently with one of my friends, Zaid. This links us to the, there we go, this is the website. It's a abstractive text summarizer which uses a deep learning model, which is based on Pegasus. Sort of like an a variation of transformer model. Pretty cool. Pretty cool stuff. Oh yeah, what was I doing? API, not here, I guess model. Here we go, this is the Docker command I need to run. So I think we'll go more into Docker in the next chapter as well. Yeah, it's coming up. But Docker containers are just really like so nice because it makes it such that wherever your container is, all of the packages that are in your container will work on any system. So sometimes I have problems with my global packages, right? For example, TensorFlow. TensorFlow has many different variations. There's several versions always just constantly being updated. I think TensorFlow is releasing 2.5 next, and 2.4 released like a few months ago. So software is constantly changing, and in order to protect all of your code in like this bubble where like basically the evolving technology shouldn't affect what your code does, so you create this bubble using Docker, which is kind of like a container, and you put all of your dependencies and all of the software that you're using at the current time period into this container. So it's kind of time-stamped. So once your software is time-stamped, no matter if newer technology comes out, your container is still going to run because it's using that original software that you used to build the code. Speaking of that, let's check my Docker containers. I think it's Docker image. Docker image A. Wow, okay. Remembering all of these Docker commands. How to list Docker image. I don't know how many times I've searched this up. You can see it's like highlighted purple because I keep clicking on it. Docker image ls. All right, so I think we're gonna use this version with Jupyter. And to run the Docker container, we're gonna use this command. So this command just makes sure that all my GPUs are running and the working directory is kind of uploaded into the container. Publishes the Jupyter notebook at port 8888 and also publishes the tensor board at this port. And this is just the name of my container. So if you're just starting out with ML, I don't recommend you using a Docker container to run your applications. I just recommend that you pip install like TensorFlow, and that should be fine for you. For me, I need to make sure that my GPU is being utilized so I get the most efficient power. Okay, this is a .py file right now. I think I'm going to make a notebook. And let's move this over here. Actually, let's keep it here so we can copy paste code real quick. Let's go back to our LSTM model. Let's name this LSTM model. Copy paste our imports. How do I make this markdown? I forgot the shortcuts. I think it's just 1. I just click 1. There we go. So imports, and then copy paste this and that. Okay, so we have to pip install. Since we're in a Docker container, my global variables don't get copied into the container. So it protects my container from my global variables. So since that happens, I have to basically pip install whatever's not included in the Docker container. That includes TensorFlow datasets. What's the pip install for dataset? TensorFlow datasets. Here, we'll copy this. Let's close this and this. And paste it here. That should download datasets into the container. Now this should run. So then copy paste the in this graphs. And now I'm going to name this input pipeline. I really like using Jupyter Notebook. It makes things very visually appealing and also really easy to debug. Whereas if you have a .py file, you need to like figure out like where the error is happening, and also sometimes it's just very hard to visualize input on the terminal. Okay. All right, I think we're up to track now. And it's downloading the dataset. So what were we following? Not this one. Yeah, this one. Move this over here. Let's close a couple tabs that we're not using. I have a pretty bad habit of just opening a lot of tabs. It's still downloading. Or I think I set the progress bar to false, right? Where did I say that? Disable progress bar. So I think it's not going to show up. Oh, but it should print the outputs once it's done. Yeah, it's still running. You can tell by the star. Let's just continue for now. All right, next shuffle the data for training and create batches. Oh, let me turn on my light. Okay. Okay, there we go. We got our output here, which isn't really the greatest format. So first we have our tensor, and then we have our text and our label. I think if it's 0, then it means it's a positive connotation, and if it's 1, it's a negative connotation. Oh no, it's the opposite. This was an absolute terrible movie. So 0 means negative connotation. And I think 1 should be a positive connotation. We'll keep that in mind for later. Buffer size, set that to 10,000. Batch size, set that to 64. Then shuffle our datasets. Train underscore data set dot shuffle. Buffer underscore size. All right, my shortcuts don't work here. Set the batch size. Refetch. What is this? tf.data.autotune. I'm not really sure what this is doing here, but it should be shuffling the data set based on our buffer size. We've set that to 10,000. We've also set our batch size for training to 64. And I'm not sure what prefetch does. Data.autotune. Better performance, which will prompt TF data runtime to tune the value dynamically at runtime. Provides benefits. Build flexible and efficient input pipelines. Okay, cool. I think that's what it does. What was that thing called again? The auto tune. The number of batches by a single training set. You could either manually tune this value or set it to auto tune, which will prompt tf.data runtime to tune. Oh, okay, cool. So I guess this makes it easy for us because when we're deploying it in our application, we won't run into input errors where the sizes aren't matching up and stuff like that. I think that's what it does. Test data set. Batch transfer size. Then we're going to do the same thing here with the prefetch. All right, and then what are we going to do here? Print it again. But here we have 3 labels. We're printing 3 instead of just 0 to 3. Oh, okay, yeah, this is just, we're grouping it together. So we're taking 3 at once. So for we could just copy paste this. It's almost the same thing. Example NumPy, where you're going to have to specify it as a list. Let's do list comprehension. Cool. Let's add a colon here. Make it look good. Also, print new line after this. No, print should actually print in a new line. Too many what? Hold up. It should be multiple labels. We're gonna have to print, say it prints in a new line. Array is one-dimensional, but 2 were indexed. We did run this cell. Train dataset dot take example dot numpy. Oh, there's no comma here. My bad. It's a one-dimensional array, not a two-dimensional array. It's not the prettiest looking, but it did take approximately 1, 2, and 3. We can tell by the B's. There's 3 texts in here, and then of course 3 labels. So the first one is a positive connotation, favorite. We can see that, so it's 1. The second one should be negative. Third one is also positive, so it says enjoyed. And we can see the second one somewhere here. I had high hopes, but it's probably going to be like That didn't make much sense to me. So it's very subtle. You can see that here. It's not directly using negative words, but it's able to pick up that. Oh yeah, here. Awful. Did an awful job in that movie. So yeah, it's very subtle, but it's able to make out that this has a negative connotation. That's a cool thing about deep learning. It's able to abstract very high level problems. Next, we're going to do the text encoder. So all of kind of like input models into any sort of text-based deep learning model, the text has to be encoded because we can't feed strings into deep learning models. Machine learning is built on numbers, so we always have to convert these letters and words into numbers that actually make sense, where we can pick out the patterns in these text, right? So we have to make sure that our model is able to understand the language which we use with letters and text, but we have to convert it to numbers so that it can understand. So to do that, we're going to create the text encoder. Set the vocab size 1000. I'm going to create an encoder. Encoder just encodes the text. Pre-processing. Use a text vectorization. Basically, it does exactly what I just said, where it takes these inputs, which is text, and creates vectors out of them with numbers. Max tokens. And we're going to specify the vocab size here. Encoder dot adapt train dataset dot map. Use a lambda function. Label as text. I'm not too sure what the adapt function does. Adapt method sets the layer's vocabulary, the first 20 tokens. After padding and unknown tokens, they're sorted by frequency. So I guess it just processes the information. Did we not import encoder? Do we spell it differently? Okay, what's next? Vocab. NumPy array coder dot get vocabulary, and then we're going to print out the vocab. The first 20. Cool. So here's what we did. We broke up the string into words, and we can see the vocab here, which consists of words. And we process that into an array, a NumPy array to be specific. NumPy encoded example. Yep, and here we're able to see a visual change between the strings into numbers. Awesome. And we just encoded the example, and I think example, where did we specify example? What? Where did this come from? Oh, okay. So from this for loop, should you even contain this value? I thought the for loop variables get eliminated after the for loop is done. Like the scope of this variable should be local to this loop. But I guess it's not. Interesting. So count up to 3. What are we going to do here? With the default settings, the process is not completely reversible. There are 3 main reasons for that. Default value for preprocessing standard argument is lower end strip punctuation, but limited vocabulary size and the lack of character-based fallback results in unknown tokens. Oh, and the unknown tokens are seen here. I think it's this. It's this list of U and K. And it's just displaying that. Are we not going to process this? With the default settings, the process is not completely reversible. Okay, yeah. So, I mean, we can convert it to numbers, but converting it back is going to be difficult because some values are going to be turned into unknown values. That's what it's showing here, where it's showing the original text, but when after converting it into the vector form and trying to convert it back, we see their unknown variables. So we're not able to restore the string fully. I'm going to skip that for now. Create the model. Okay, I think it's been an hour. It's been an hour. 6:35. Yeah, 6:30. I think I'll take a little bit of a break and then maybe code up the model and try to finish training it. And we'll stop there and finish up with defining what the goals are for tomorrow. Oh man, I'm gonna have to start my internship soon. I need to figure out what I'm doing for that and coordinate with my mentor. It's a lot of work coming. And of course, on top of that, college is very unpredictable. They haven't really given us the best options for our finals, I guess, due to the pandemic situation at the moment. India is having a very rough time with COVID, and we'll see how it plays out. So where were we? Let's skip this and get to creating the model. So here's the model. I'm going to create using Keras. Sequential. we're going to have the first layer as the encoder. And then we're going to have our embedding layer. TensorFlow keras.layers embedding. Specify the input dimensions. So this should be dynamic based on the input. Output dimensions is 64. Mask 0 is set to true. I'm not too sure what exactly that does, but probably some sort of masking process. All right, now we're going to have a bidirectional layer. Specify our LSTM model here. 64. And then we're going to have two dense layers. Dense. This one will be 64 with an activation of a ReLU function. And then our last layer will display the output or contain the output. There's that dense, and it's just going to be 1. Okay. Please note that the keras model here is used here since all the layers in the model only have a single input and a single output. In case you want to use stateful RNN, you might want to build your model using the keras functional API. Okay, that's fine. Embedding layer uses masking to handle the varying sequence lengths. All the layers after embedding support masking. And that's just showing that it contains the masking to confirm. So here it's showing the difference between without padding and with padding. And the result should be identical. So it doesn't really matter, I guess, if you have padding. It's cool. All right, let's compile the model and begin the training process. What's wrong here? Did I not import TensorFlow? It's gonna... No, there's a missing comma here. That's why. And I spelled input wrong. And output wrong. Cool. All right, it compiled. Now we gotta write the compile. Set the loss function as binary cross entropy. Set the optimizer. As Atom. Metrics accuracy. So I guess in the later on stages, we're going to be deploying, oh, it's going to show the accuracy when we're, yeah. Oh, metrics you use to compile the model, okay, to train the model. We're going to start training. Maintain a history so we can display it on the matplotlib pipeline. And this should use my GPU to train, so it should go pretty quickly. Spelled test data set wrong. Data set, there we go. Train function. What's going on here? Function stack call. Where is it happening? Validation steps? Did I spell that wrong? That's no good. Test data set. We have our train data set. We have our epochs. We have the model, it's compiled. All right, time to Google. Memory leak. Oh my god, that's a mosquito. Sorry if that was loud. Setting GPU growth. That's the issue with running it on several different hardware. Sometimes it's just not optimized for your hardware. And I do have a 3080, so it's fairly new. It could be an issue with that. Let's try this. That did not fix it. Oh, spoke too soon. Wow. Works on one machine but not the other. Software. He's running this on a 1070. Let's check our settings. What's NVIDIA SMI? All right, let's see. Our CUDA version is 11. CDNN. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. 11. This is 10. There we go, we're using 11 here. Just have to make sure that my software matches up with these guys, so their solution works for me. This is running over time and starting to get pretty annoying. A lot of people are saying this fixed the problem. Oh man, this might take a while. We were so close. All we had to do was train and print the loss in accuracy. So close yet so far. Let me just double check my values. Font size 64. Buffer size 10,000. Should we create the buffer a lower value? That creates errors. If we lower the batch size, I mean, do we have to lower the vocab size? What is going on? Let's rerun this. There's a problem. Here, we're gonna change this to, and we're gonna have to run from here. Okay, it's working so far. Nope, it does not do anything. Alright, this may be a problem for tomorrow. I think I'm going to be stuck on this for a while, especially if there's no direct solution. So yeah, it is using my GPU, I know that for sure. I just confirmed it right there. So we're setting the memory growth of this GPU to true. Physical device cannot be modified after initialized. That's no good. Well, none of this worked for him, apparently. Alright, I'm gonna end this here. Try to debug a little bit more off stream. And we'll come back tomorrow and deploy it. Okay, so for tomorrow's goal, there's a train or code LSTM model. Well, we started. Well, we finished most of the code, so I'm just going to leave it as that. Next up, I think we're going to have to build the UI using Streamlit for the LSTM and deploy and we also have to train the LSTM model. Cool, so those are the goals for tomorrow, and let's see, day 4. So I'm honestly kind of not sure if I'm going to be able to finish this tomorrow. So I think I'm going to continue and give myself an extra day to finish day 3. But if we do finish day 3, for day 4, we're going to continue into Docker. And we're going to learn about Docker. All right. Thanks for